All right, I'm going to do a little screencast here that will help you understand these AP practice problems, I hope, or at least help you get them started, that are due on Monday. The first one is a problem where you've got this two objects, one at the top of a ramp, one at the bottom of the ramp, and it tells you that the small block is released from the top. It's a curved, frictionless ramp. Again, I highly recommend you guys read these problems carefully. Highlight or underline the important points in each one, because on a test, when you're going fast, you can skip over stuff and not realize that it's important. So if you slow down, read it carefully, highlight stuff that's important, it's going to help you a lot. It's a curved frictionless ramp, meaning there's no external force of friction on this in this situation. The block slides down the ramp, and they give you the speed with which it's moving when it collides with a larger block, 3.5 v0. So I showed that up here in my little diagram that I drew. The block M at the bottom at 3.5 v0. The larger block with 1.5 m moves to the right at speed 2v right after the collision. So I have that here. They were kind of nice to you, because if they gave you this 3.5 v0, this original one that I highlighted up here, and you knew the masses of both of these, you potentially could calculate the final velocity of each mass individually. But anyway, they give you the 2v0. You could have used momentum to solve some of this, but they gave you enough information where you don't have to do that. So you have the velocity of the 1.5 m mass is two times this v0 constant, and it's going to slide to the right a distance of d before coming to rest. So I drew that on my diagram up above, and they want us to solve for the value of the kinetic coefficient of friction, on the larger block and the surface on which it slides. This is very similar to what we did in class today with the spring and the sponge, only in this case the block is moving. It's got kinetic energy at the beginning, not elastic energy. So keep in mind you have to define a system. You have to decide what's in your system, what the initial conditions are, what the final conditions are. And all I'm trying to do is I'm trying to come up with an expression for this coefficient of kinetic friction here in terms of all these other variables. So the things that can be in my answer are the variables that are given. I can have V0, I can have H, I can have D, I can have, what else? Fundamental constant, which is G. I can have the letter M for mass, whatever I need. But they're just trying to get you to come up with an expression for that coefficient of kinetic friction. So I'm not going to give you any more information on this, because it's very similar to what we did in class today, and I hope you can get through this one with just kind of seeing the diagram and defining your system correctly and deciding what kinds of energy are in the system over the course of the before and after. All right, here's the second problem. It's a pendulum problem, and we haven't worked with pendulums yet this year, but a pendulum is just a heavy object at the end of a string, and we treat the heavy object down here as if it was a point mass, okay, which means all this mass is concentrated at a small point. And it wants you to draw a force diagram below and label the forces on the bob in the position above. I kind of did that for you here. I didn't label the downward force. I'm assuming you can do that. I distinguished between the horizontal tension force. I called it TH. Those are two different strings, so they can have different tensions. So the one to the right I called TH. The one up to the left at an angle I called just T. So it asks you to calculate the tension in the horizontal string in part B. So to calculate the tension in the horizontal string, you're going to have to come up with some Newton's second law equations. And actually, since this object is at rest, your force diagram should be a balanced force diagram. So go ahead and add components to this diagram. Solve for TH in terms of, well, not in terms of anything. You can actually get a number, because they give you an angle here, they give you the mass of the object itself, and believe it or not, that's enough information for you to be able to calculate a number for the horizontal tension in that string. The last part of this, in part C, asks you to calculate the speed of the pendulum when it gets down to this bottom point right here. So at some point, the pendulum swings down after the string is cut. So someone cuts the string and it swings down. This is an energy, most easily solved as an energy problem. So part C, you want to use an energy approach. All right, and you want to define the system. Believe it or not, well, not believe it or not, but this is changing heights from here to here. So it's higher when it's pulled back, it's lower when it's at the bottom. So you've got a change in UG. So when you define your system, you better include the Earth in that system. The kind of energy you have at the beginning, which is right after the string is cut. This is the initial situation. This is the final situation when it's at the bottommost point. The initial situation is UG. The final situation, certainly it's moving. It's got a good velocity down here, and that's what I want you to calculate, is its velocity at the lowest point. So we're trying to calculate that final velocity. There's definitely kinetic energy because it's moving. And at the same time, I would say your lowest point should be your reference UG 0 point. So I'm going to say no UG at the end. So all of the UG at the beginning, 100% of this is converted to kinetic energy at the end. So set up that equation, and you'll find the only thing that you need to know is what the change in height is from the initial to the final condition. And you can use trigonometry to figure that out. There's enough information with the 2.3 meter long rope and that 30-degree angle to be able to figure out the difference in height from this point to this point down here. Okay? You can use trig in this triangle right here. That is this side, this side. You can use some trig there to figure out the change in height, initial to final. And once you find that change in height and apply it to the equation that you should have written down, you can find the speed at the bottom. Okay? This is similar to the problem we did in class with the trying to find the minimum height to release a car that will just barely get around the loop. Only this is a little, like a bullet that enters into a block. You know, it's shot into the block, and then the block and the bullet embedded in it go around this loop-to-loop. So they give you some information about the block of mass 2m. It's initially at rest, so you highlight some of this stuff. The surface contact between the block and the loop is frictionless. That's also important. And it strikes it horizontally with an initial speed of v0 and remains embedded in the block as it goes around the loop. So it asks you three things. The speed of the block and the bullet immediately after impact. That's a momentum problem, okay? Trying to answer the question of after these two things interact, you know, this collision of the bullet and the block, after that interaction, how fast are they moving together? That's a momentum question. What's the kinetic energy of the block and the bullet when they reach point P on the loop? Okay, that's obviously an energy question, which we can answer once we know the velocity of the bullet and the block. And last is, what's the initial speed of the bullet? What's the smallest speed the bullet can have so that the block and the bullet are to successfully execute a complete circuit around the loop? So the smallest speed of the bullet will give you v min of the bullet in the block. I'll just draw a little bullet in here like that, that the bullet's embedded in the block. So that would mean the bullet's minimum speed down here would give the bullet in the block the minimum speed at the top of the loop to be able to execute a complete circuit of the loop, meaning at V min. Remember in class today what we said? There's something that is 0 at the minimum speed at the top of this loop. That's also an energy problem. I'm going to leave it at that, and I'm going to hope that you're able to get most of that done. All right, last one. So this is a massless spring with they give you a spring constant. It's also called a force constant. It's the same thing, of 400 newtons per meter, fastened at the left end up here to a vertical wall. Block C, which has a 4 kilogram mass, and block D with a mass of 2 kilograms rest on a horizontal surface with block C in contact with the spring. It's not attached, but it's in contact with the spring, but it's not compressing it. Very important. So in this initial condition, the block C is not compressing the spring at all. It's relaxed. It's in its relaxed length. Then it says block C is then moved to the left, compressing the spring a distance of a half a meter, and it's held in place while block D remains at rest. And it tells you to use 10 meters per second squared for G. What's the elastic energy stored in the compressed spring? I'm sure you can do that based on the information given, the K value and the amount of the compression. Down here it says block C is then released and it accelerates to the right toward block D. The surface is rough and the coefficient of friction between each block is 0.4. So you know you've got friction present. The two blocks collide instantaneously, stick together, and move to the right. So the blocks hit each other and then move together. That sounds like a momentum problem. Move to the right. Remember that the spring is not attached to block C, so once block C gets back to this position it is in figure 1, the spring is not attached to it anymore. All right, so it's not in contact with the spring, and there's no spring energy in the system. Okay, we're supposed to find the speed of block C just before it collides with block D. Well, that's an energy question, and that's not too hard. If you know how much energy was in the stored spring initially, you should be able to figure out how much kinetic energy block C has based on, or the speed of block C based on how much elastic energy was stored in that spring. Okay. Then it says, what's the speed of blocks C and D just after they collide? Well, that's a momentum question. So once you know what the speed of block C is, when it gets to the point where it just contacts block D, it's a pure momentum question to calculate the speed of C and D after they collide. And remember, they stick together because it says the blocks collide instantaneously and stick together right there. Okay, and move to the right. So I should have highlighted that earlier. But you should be able to figure out how fast they move together after they collide using momentum. The last part of this is the horizontal distance the blocks move before coming to rest. Okay, so now as they come to rest, it's a question of how much of the initial energy they have when they were moving together is present when they stop. And this is exactly what we did in class today, only instead of a ball and a sponge, it's two blocks hitting each other. So if you followed along in class today, what we did on problem 29 from the end of your book, you should be able to figure out an expression for the horizontal distance the blocks move before coming to rest. Obviously that's an energy question, and we've got friction, so the surface here has to be part of your system. Remember how to calculate the amount of increase in internal energy, the change in internal energy. It's equal to F times D. And I think they don't give us an expression for the horizontal distance, but that would be this D right here. Okay, so you have to solve for that D in part D down there. Okay? I hope that helps you. We'll go over these on Monday briefly in our morning Zoom meeting on Monday, and then I'll see you on Wednesday. Have a great weekend, guys.